The design and simulation procedures for distillation are based on two important concepts. The equilibrium stage concept, introduced in 1894 by Ernest Sorel, and the concept of the Murphree stage efficiency, introduced in 1925 by E.V. Murphree. Murphree wrote in his seminal paper, "The concept of the theoretical plate does not offer a satisfactory basis of calculation for rectifying columns when the mixture being rectified contains more than two components. And even for some calculations on binary mixtures, its use is not satisfactory." This is the definition of the Murphree component efficiency for a distillation tray. It is the ratio of the actual composition change divided by the composition change that would result if the vapor leaving the tray were to be in equilibrium with the liquid mixture leaving the tray. For a binary mixture, since the mole fractions add to unity, the component efficiency for component 1 should be identical to that of component 2. Furthermore, for a binary mixture, the component Murphree efficiencies are bounded between the values of 0 and unity. For mixtures with 3 or more components, there is no requirement that the component Murphree efficiencies be equal to one another in the mixture. Now, there are important consequences of unequal component efficiencies on distillation trajectories experienced in, say, azeotropic distillation. If the component efficiencies are equal to one another for ternary azeotropic mixtures, distillation boundaries cannot be crossed. I explain this in the following slide. An alternative title to this presentation could have been, "Can distillation boundaries be crossed?" Let me explain that a little bit further. Let's take a specific example of a ternary mixture of acetone, water, and ethanol. Acetone is the most volatile of the three components, with a boiling point of 329.7 Kelvin. The least volatile component is water, with a boiling point of 373.2 Kelvin. Ethanol is the component of intermediate volatility, with a boiling point of 351.6 Kelvin. Water and ethanol form an azeotrope that has a composition that is roughly 90% ethanol and 10% water. The azeotrope boils at 351.4 Kelvin, slightly below the boiling point of ethanol. These pink lines are called residue curves, and they map out the distillation trajectories that the compositions in a distillation column must follow, where the distillation column to operate under thermodynamic equilibrium conditions, in other words, following the theoretical plate concept of Sorel from more than 100 years ago. We note that the residue curve maps do not cross the thick black line, which is called the distillation boundary, that connects the acetone apex to the azeotrope composition. Put another way, if we follow the concept of theoretical stages and residue curve maps, a distillation column, feed mixture anywhere here, cannot be distilled to produce pure ethanol. That is only possible to produce pure ethanol if we have feed mixtures with compositions on the left of the distillation boundary. So asking the question, can Murphree efficiencies assume negative values, is analogous to asking the question, can distillation boundaries be crossed? Now, to answer this question, we need to abandon our traditional approach to mass transfer following Fick's law, and we need to adopt a more rigorous description of mass transfer in the vapor phase, mass transfer in the liquid phase, in order to ask and understand the question, can distillation boundaries be crossed? So let's first bury Fick's law. This is the experimental setup used by Martin-Springer. All the experiments were conducted at total reflux conditions in a column that consists of a glass column that consists of bubble caps, and the vapor compositions at the various locations shown here, and the liquid compositions were monitored. Samples were taken and the compositions determined. This is a photograph of the distillation apparatus. Details will be found in several publications with Springer as the lead author. In my previous presentation, I had analyzed the experiments of Martin-Springer carried out in a distillation column under total reflux conditions for the ternary mixture of water, ethanol, and acetone. The experimental data of Springer shows that the distillation boundary, shown by the thick black line, may be crossed. Here we show the compositions of the 11 trays in blue, ranging from the reboiler to the condenser. If the trays were to operate under equilibrium conditions, the composition trajectories must follow the residue curve maps shown in pink, and no boundary crossing is allowed if the stages were to operate under thermodynamic equilibrium conditions. The actual conditions, we note that as we move up the column from the reboiler to the condenser, the compositions cross the distillation boundary. Mata and Springer examined 4 to 5 different mixtures in the distillation column shown in the previous slide. And I just show one set of experiments for the system acetone, water, ethanol. The experimentally determined composition trajectories are shown by these blue circles. And the first thing to note is that this is the reboiler composition, and this is the condenser composition, but the condenser composition is on the left of the distillation boundary. So the boundary has been crossed in these set of experiments. From the experimental data for the various trays, the distillation, the driving forces can be determined, and the Murphree component efficiencies can be calculated using the experimental data on the measured composition entering and leaving the tray, and the vapor liquid equilibrium thermodynamics that were determined using the NRTL model and the Deschema database for the experimental data. The component Murphree efficiencies are plotted here for various stages in the 12-stage column, condenser being stage 1 and reboiler being stage 12. The red circles are for water, the blue triangles are for acetone, and the green squares are for ethanol. Ethanol is the component with the intermediate volatility, and since it's the component with the intermediate volatility, its driving force changes in sign from negative to positive depending on the location in the column. And the component efficiency for Murphree efficiency for ethanol assumes negative values between stages 9 and 11 on stage 10. So a short answer to the question posed at the beginning of this presentation: yes, Murphree efficiencies can be negative and distillation boundaries can be crossed. But the more important problem or task is to try to calculate the distillation trajectory, taking mass transfer effects into account, and using the Maxwell-Stefan model for the vapor phase, for the liquid phase, using all the details that were presented in the foregoing slides. Starting with the experimental value of the condenser composition, if the equilibrium stage model were to be used in simulating the distillation column, the trajectory that would follow is shown by the pink line here. The actual experimental data indicated by the blue circles require the use of the Maxwell-Stefan equation for the vapor phase and for the liquid phase, and the resulting model, normally called the non-equilibrium stage model or NEQ model, also referred to as the rate-based approach to distillation design, is able to accurately follow the experimental trajectories. The details are provided in the publications listed here. The important message to emerge from this presentation is that for modeling azeotropic distillation columns, the use of unequal models with Maxwell-Stefan diffusion formulations is of vital importance.